Hi everyone and welcome to our podcast. Today I have the pleasure to have Amrita and who is also from Kharagpur. We grew up together and today she'll be talking about battery modeling. She held her PhD in mechanical, applied mechanics, and now she is a battery modeler at a reputed company. Mostly we'll be discussing about data set and modeling technologies today and what are the challenges. She'll also share a case study with us and I hope we can learn a lot from her. So without further ado, Amrita, welcome to the podcast.
Thank you so much, Tanishta, to have me here. I'm really grateful. And myself, Amrita, and I have completed my PhD last year, and then I joined Volvo Energy in the R&D group of Volvo Energy. So, as a battery modeling engineer, and battery modeling, as we know, as of today, has like a lot many, you know, uh, uh, a lot many domains inside it. So there are, simple models like empirical and
Mm-hmm.
which are which can be solved very fast, which are not computationally very expensive,
Mm-hmm.
which are used in the BMS and all. Then there is another part which is the AIML data-based modeling, where we
Mm-hmm.
see different vehicle data, how they have been used, and we do not go into much details of what is the chemistry of the battery, or which even like which battery, or what is the different physical and chemical properties of the battery. We do not go into such details. We just see how a battery is behaving based on how it is being used by the user.
Mm-hmm.
And then based on that, we try to, so if you have like 1,000 data of these batteries, then you can basically predict. If I give you another like 1,001 data, then you can predict what can be the life of that battery based on how it is
Mm-hmm.
being used right now. So that is like a database modeling. I myself am in electrochemical modeling in Volvo Energy. So in
Mm-hmm.
electrochemical modeling, there is like too much of detailing. Like you need to know all the physical chemical properties of the battery, what is going inside, and so based on the chemical reactions, we represent all these chemical reactions in terms of partial differential equations. Then we use some
Mm-hmm.
software to solve these. So this is very computationally expensive, but it is known to be like the most reliable one when it
Right.
comes to a battery model.
So can I
So
ask you
this
one
is like,
question,
yeah.
Amrita, since you talked about battery modeling? So what kind of equations do you, if you can just hint on what kind of equations you solve and what are the models? Is it like you solve finite element models and something like that? Solve those
Yes,
equations through that? If you can give a little bit hint
y-
on that, like some explanation on that.
yes. In electrochemical modeling, it is like, because these are all partial differential equations, so
Right.
time dependent as well as space dependent. So you consider the entire battery, and say it has cathode anode separator, all these things,
Mm-hmm.
and the lithium ions, these are passing from the cathode to anode and then back to cathode during each charging and discharging sessions.
Mm-hmm.
So inside the battery, at any point of time, and at any point in space, the equations will have certain values. So these are like both temporal and spatial equations, and it is solved through FEM using all these softwares like COMSOL and
Mm-hmm.
Autolan. All these are different platforms. Even like through MATLAB also you can solve, but because these are, I mean, these are multi-physics problems. It is
Mm-hmm.
actually electrochemo, mechanical, and also thermal part is there. So
Mm-hmm.
since it is like too many physics at a time, so it is easier to solve in certain software platforms rather than writing your own code in MATLAB or using Python and all these. But nowadays we also have this PyBAM, which is Python-based battery modeling software. So this is also helping. So basically, yeah, these are solved by FEM.
Oh, okay, I see. So,
And coming to like the, I mean, just in a very short this thing. So coming to empirical and data-based modeling, however, we do not use this partial differential equations and all these equations. Those are very simple. In empirical modeling, for example, we consider the battery as a black box. We don't know inside what it is there. We just give the inputs like voltage, current, and all these things. We give a lookup table, for example, how the voltage is changing at different charge stages, like SOC we call it, state of charge, at different charge percentage, how the voltage is changing. So this lookup table is fed into it, and all these are fed as an input. Then as an output, you get different results. And inside the battery is, you know, different lumped parameters are used to define the battery model. These lumped parameters are basically representative of the underlying physics. For example, in a spring mass damper system, you can represent it with a voltage resistance, right? So in that way, anywhere if there is a negative force, like a friction kind of thing, you place a resistance, and then you try to, it is not actually a resistance, but you represent it in that way. So this is kind of an empirical model, how it is built. So, and data model, you already know, like,
yeah.
So this is the thing.
Okay. And so I believe you wanted to share a case study. Maybe I can share the screen and we can talk about that case study.
Yeah, sure. So, yes.
Yeah. So what do we see here, Amrita?
Yeah. So first of all, I'll give the credit to the data analyst team of Volvo Energy here. It is their research basically, but because you were more interested to know about the data problems that we face in our day-to-day research, so I asked for their permission and then tried to. But this is a very generalized problem. I'm sure many of the EV R&Ds face this kind of a problem. So you see, when we try to understand try to understand the data of the battery, how it is being used, and all these things. So we get this data from the BMS, which is the battery management system.
Okay.
So BMS logs the data in this way. It is just an example. It is a little complicated when you see it. It has some different format, but overall, this is the information that you get. You get a timestamp, then you get the mode of operation, whether it is charging or discharging. Only when the battery is running, you get the data. When it is at rest, you do not know anything about it. Then you, within this timestamp, what is the minimum SOC, what is the maximum SOC? SOC means state of charge.
Okay.
State of charge. So basically, like, you have your cell phone, right? When it goes to 5% charge, it put it on charging mode.
Yeah.
Then when it goes up to say 90%, you take it out. So here, as state of charge SOC is 5 to 90%. So if I give a timestamp, it will show minimum SOC as 5%, maximum SOC as 90%. Then SOH, which is the state of health. So state of health is like the battery's health. When it is new, the state of health is 100%. Say after 2 years, your phone battery, it doesn't go for the entire day, right? You have to charge twice or thrice. So that means your battery has gone, say, up to 80%. It's not up to its entire fullest capacity.
Yeah, right.
So that is the state of health. So say it is 90% or something, and then within this timestamp what is the minimum current, what is the maximum current.
Mm-hmm.
So during the charging session also, depending on how the this here we are talking about vehicles, so how the vehicle is being charged at what charging protocol, so the minimum and maximum current will vary. During driving, it is very important because you do not always drive in the same speed, right? Because the uh, road terrain will be different. Your sometimes some vehicle will come in front and you will brake. So
Yeah.
the
So it also
current
depends on
requirement,
individuals driving characteristics
exactly.
also, right? Mm-hmm.
Right. So, in that way, the current requirement, the power requirement during driving will be different. So, the minimum and maximum current will be different. And then it shows the energy during this session. So, if it is charged from, say, 5 to 90% state of charge, then what is the energy that is gained inside the battery?
Mm-hmm.
So, these are the few information that is logged into the BMS. Now, why I would like to stress why this much information is not enough. Say you have this information for two vehicle batteries, A and B.
Mm-hmm. Right.
So
Yeah.
these batteries have same running time. That running time means both have been running for say around 2 years now,
Mm.
so almost same
Yeah.
time for operation. And then both of them are seen to have the same charging pattern, like very mild, say only like overnight charging they're doing. So it is so both of them have similar charging patterns. Similar discharging patterns also are seen because maybe it is running in the same region. For example, same buses will have same charge discharging patterns if it is running in the same route,
Mm.
because the road terrains will be same. Also the ambient temperature will be same in a certain area, right? So the battery temperature might also be same.
Mm.
So say all these things are same for these two batteries. Even then, the SOH, that is the state of health, is seen
Mm.
to decrease in a different way for A and B. Now, this is something which, when the battery data analysts analyze these data, they see a lot of these cases and
Oh.
they fail to understand
Huh.
why this is happening. So, two of these things are because of this gap in data.
Mm.
First is we need to correlate the battery data with the vehicle data. Why? Because even
What
though
do you mean
uh,
by vehicle data, Amrita? So
right.
what kind of vehicle data are you looking for here?
So vehicle data means, uh, for example, the speedometer reading, then this terrain, where it is, like the latitude, longitude, so that you know the altitude of that place. So if a vehicle is running in a mountainous
So,
region,
so
and
just a question, maybe a stupid question. So,
no,
will it also be affected if it's running through a different traffic, right? The maybe the traffic condition is
yeah,
high during daytime and it's low during night. Will that
yeah.
also affect? Okay,
Yeah,
that's
yeah, yeah. Because number of times you are, putting your brake, that
right.
will get affected. Okay. So then also some people will drive very rashly, even in traffic, and they will put very harsh brakes during traffic. So all these things, all these small, small things will add up to, like, if you do it for once or twice is fine, but if you do it for a very long period of time, your
Yeah.
battery health is going to get affected because of the usage.
Oh.
So these things, like the different vehicle data based on the location, the
Here,
speed, and
just another thing that comes to mind is it also kind of has some seasonality, maybe in a hot weather or a cold weather, or
yeah.
does it? Okay, so there's this lot of factors coming in, I see. Mm-hmm.
Yes. So when we talk about what kind of things stress a battery, like we
Yeah,
call those battery stresses, they are actually, I mean, five or six more. I mean, the most stressful things on the battery are five or six parameters. For example, the
oh,
charging rate. If you are doing fast charging or normal charging, on a daily basis. That charging rate is one of the factors. Then, as you mentioned, temperature is a factor. So
Yeah.
if you are driving the vehicle in India, I would say in Rajasthan and in Ladakh, the degradation will be different for these two.
Hmm.
Similarly, the sock window, like till till what percentage of battery you are discharging. If
Hmm.
you are if you are discharging up to 5% daily, then it is called as deep discharge. So it is harmful for the battery to some extent. Then every day you are charging up to 100%, keeping it at rest for the entire night, and then driving during the day, coming back, then again charging up to 100% and keeping it. So all these things matter a lot. This is a stress again.
Oh,
So that is like battery data, and you do not have so mind it, you do not have so many information from this BMS data. So
right.
that is the second gap also, that in this data you see minimum and maximum current logged in, right?
Hmm.
But you do not know, say suppose in driving, you know that 12 ampere has been reached
Hmm.
at some point. Now, 12 amperes, say for this battery, is a very high current. But you do not know from this data itself that how many times that 12 ampere has been reached. Because it does not show these violation counts. It just
Hmm.
shows the maximum current. Also, uh, how long it was in that condition. That also
Hmm.
you do not know.
Hmm.
So both the
Hmm.
frequency and the time period, both of these information are missing.
Yeah.
So these two are the gap in the data from which you do not like really understand why these two vehicles are showing different states of
Right.
health. I mean, given that all of these things are same: running
Yeah.
time, charging
Uh-huh.
pattern, battery temperature, everything.
Hmm.
So coming to the challenge part, like this is gap fine, but I mean, if I even like try to reduce the gap or solve it, what
Hmm.
is the challenge? So the challenge in correlating the battery data with the vehicle data
Hmm.
are two. So first of all, the format in which the battery is logged in BMS is different from how the vehicle data is logged. So
Hmm.
because these two are different, so you do not know like how to merge these two files. This is one of the very big challenges,
Hmm.
because battery will come from, I mean, a different manufacturer. Different, I mean, it will be assembled differently. Then these vehicle data will be done by the way, I mean, the EV manufacturers. So
Right.
there should be a common platform to merge these two data. So the formatting should be done in such a way so that we can merge it easily. This
Hmm.
is first. Second is the frequency of the data logger. So how uh, this vehicle data is logged in and stored, this is different from how the BMS data is logged in and stored. So once you have a timestamp of, say here it is 1:10 p.m., right? But
Yeah.
maybe there are like 10 I mean, within this time, 10 times the vehicle data has been logged. So
Hmm.
it is very difficult to make these correlations. So these are the two main problems. And then comes the challenge with the data logging about the time and frequency. So
Do you
this
mean
is
by how
very, I mean,
frequently the data is logged, or something like that? Or
no, no, no.
no? Okay.
The second gap I'm coming to, that
Okay.
I do not know like how many times the maximum current has been
Hmm.
reached,
Reach
or
to 12
how
amperes,
long
right?
it was there,
Hmm. Hmm.
how
Right.
long it was running at that maximum
Hmm.
current. So the challenge in that is like the huge size of data and the storage and transfer of that BMS data when it is too heavy. I mean, that is very difficult. So these are few of the challenges that we are facing, and I'm sure many of the
Are
other.
there no technologies as
Mm,
such that you can, while the data is being generated, it's just transferred to maybe to a to a bucket, like kept stored in a cloud somewhere. Is this
It is
it
getting
is
stored in a cloud. It
but
is
it's
getting
just
stored in
getting
a cloud.
too big of a data, right? So you have
Yeah,
to,
yeah.
okay, roll
It is
out.
getting stored in a cloud, but then and handling so much of data is also an issue.
Okay. And
So
how much are you in general? How much is are you applying deep learning to this? Because it has a lot of context. So, like for example, there's transformers which can train on many contextual information, like the one that you were talking about, the vehicle data that got lost, which should have come along with BMS data. So how much is this kind of modeling going on in the industry or in general in research?
so I won't be the best person to answer that, because my like background is not data
Yeah, of
analysis
course.
or data modeling. Maybe the data analysts you should talk to in our group.
But do
They
you
will be the
know
best
about
person.
researchers, like if you have come across any research like that?
I'm not very sure of.
Oh,
As I told, I'm not the best person.
best
Yes,
person.
surely not the best person. Yeah.
Yeah, for that's okay. No, because it's very interesting, because with all those data, and if you can combine the BMS data along with the vehicle data, but also vehicle data is a problem. It has a proprietary data. It's very quite difficult to get that data, as you mentioned rightly.
True. Like
Yeah,
it has many like privacy things attached to it, and you cannot know the location of the vehicle and all these. So there are these things attached to it. But uh, to some extent, like sometimes it happens that you mask the vehicle number
yeah.
and know these like you mask the phone numbers nowadays, so in that way you mask the vehicle numbers and know certain information just for R&D purpose. And then it has all these non-shareable uh, some
The information can
in,
kind of, yeah. So, and coming to that, if as a data modeler, do you use any of these data? Like, for example, like any of the vehicle data in your data modeling? Like, not a
yeah, so
data-driven model, though.
yes. So, yeah, I'm not I'm not using vehicle data right now. But what happens is, like in electrochemical modeling or in empirical modeling,
Yeah.
we generally use data from the lab. I mean, experiments which are done in controlled conditions. You give a
Mm-hmm.
certain C rate, you decay the battery in certain way, and then you see and you learn how the battery is degrading in that condition,
Mm-hmm.
and correlating those control conditions with the actual vehicle data is also another challenge which we are trying to resolve right now. So because in actual like real scenario, the
Mm-hmm.
people will not use the same C rate for
Mm-hmm.
uh, charging the vehicle. Even charging is fine, but discharging is a issue. Then temperature will vary, sock window will vary, but in lab test it is all controlled. You are giving your own program.
Mm-hmm.
So but that is the basis of building these electrochemical models and the
Mm-hmm.
empirical models. But
Mm-hmm.
once you have these models, then you can club this with the actual drive cycles, so that is possible.
Okay. No, I get it, but very interesting problem. Like it's a very I'd say, as a deep learning expert, this is a very interesting problem to solve with deep learning also, because it's so much data. Data is not a problem, because many a times as we go into projects, we have data challenges, but there's abundance of data here. However, maybe there would be some modeling that can be done, architectures can be trained. So maybe we'll come to the last section. We have few minutes left, and the last section. So Amrita, you have a lot of knowledge on battery modeling, but What is your take on clean energy?
So, clean energy is a very big, very
Very
big
big.
topic. Yeah, but I would, being from a battery background, I mean, coming from a battery
Yeah.
industry, I would focus on how batteries can contribute to this clean energy, this mission of, going going through this sustainability and like net zero
While
emissions that we
we
are.
are at it, I just wanted to ask you another question. So, these batteries, are these being recycled, or because so many batteries from the vehicles, if they are, what's happening with it? If because that's also a very big challenge. If you can
Yeah.
also
So
talk about that a little bit,
I thought of like coming to it as a part of the answer for your
yeah.
question, clean energy question itself.
Okay.
So in Volvo Energy, uh, we actually are driving this circularity of batteries. So once you make a battery, you use it in vehicles, and just saying that the vehicle is you see less emissions and you get clean electricity and all these things are fine, but uh, just throwing away these batteries when it is not any more useful in vehicles is not a very clever thing to do. So there should be a definite way of managing these batteries once it reaches the stage where it is no more used in vehicles. So
Hmm.
that is what we are trying to do in Volvo Energy. One of our very big goals is to use these vehicle batteries at the end of life of vehicles to something very to make something useful
Huh.
and in low power applications. So that is what we call as repurposing. And
Okay.
then there is another sector like remanufacturing, refurbishing. So then this comes as the repurposing. And then, as you mentioned, recycling. When we cannot do anything with that battery, it is
Mm-hmm.
completely non-useful for any kind of applications, then we recycle these batteries. And this entire thing should start from the very beginning, from the manufacturer side itself,
Oh.
because how you recycle will depend on what materials goes inside the battery.
Mm-hmm.
Because if you use certain materials which are harmful and which cannot be recycled, so that makes it useless. So this entire cycle starts from the very beginning. And in so Volvo Energy was actually set up, I mean, it is a very new company actually within the Volvo group, but it has been set up with this idea to,
Mm.
close this loop, because already Volvo trucks, buses had started using the batteries. So they had started becoming electric trucks and electric vehicles, but we had to close the loop of these batteries in some way. So yeah, so that's our main goal.
Okay.
So we are
No, no,
driving that.
this was something because I do come from a geology conventional energy background, but I've done it for maybe few years ago. But because as such, like it's a big challenge for nuclear waste. But what's the challenge with these dumping these older batteries? That always triggered me, like what, because even that has to be done properly, right? But
Yeah.
no,
So
nice
in
to know about
recycle
it.
also,
Mm.
in recycle also we try to extract as much amount of the materials as possible from these batteries, and which can be used to make new batteries.
Right,
So
right.
that is the goal. But always, because chemical reactions are happening inside, so there will be some amount of irreversible reactions. So some compounds or some things will form, which so you cannot get all those initial elements out of those old batteries. So that challenge is always there. but like something is better than nothing.
Nothing, of
So
course.
that is
Yeah.
the word.
Well, Amrita, thanks for sharing so much knowledge. As you mentioned, I think we would do some follow-up podcast where we can also show some maybe take a data like even if it's a fictitious data, I think, or maybe an open source data, and maybe apply a
Sure.
little bit data like how the SOH or SOCs are calculated, or that will be also useful for our audience to see how these things work.
Yeah.
But otherwise,
Sure.
very nice interacting with you, and hope our audience likes it. And thanks again. Bye.
Thank you so much. Thank you so much.